In the quiet black of space, where sunlight thins into a pale whisper, a single sphere drifts through the dark. It is blue, delicate, and wrapped in a thin veil of air no thicker than a painter's final stroke. From a distance, Earth seems complete in its solitude, a lonely ornament suspended on an invisible thread. Yet the closer the gaze moves toward it, the more fragile it becomes, as if its oceans and continents are held together only by breath and chance. Within the troposphere, clouds gather like soft thoughts, carrying storms and the weight of seasons. A little higher, the air thins into a faint shimmer of molecules. Then, past the exosphere, warmth collapses into emptiness, and Earth's final atoms drift away into the void. Beyond this boundary, the planet's presence fades, swallowed by a silence that stretches toward the sun and far past it. The solar system sprawls around this world with an indifference carved into billions of kilometers. Gas giants circle like ancient guardians, dwarfing the Earth 1,000 times over. And still farther lies the Oort cloud, a sphere of icy fragments so vast that Earth's orbit becomes a pinprick, barely a memory. Here, scale reshapes itself. The familiar becomes small, and the small becomes immeasurable. Earth, so mighty in the stories told upon its surface, becomes an object so light it could vanish between one heartbeat and the next. So the question rises, is Earth large or small? In a universe where galaxies drift like dust and superclusters span hundreds of millions of light years, the meaning of Earth's size begins to shift. Perhaps it is a giant. Perhaps it is nothing at all. Or perhaps it is something far stranger, a world defined not by how big it is, but by where it stands in the vastness of everything else. For most of human history, the Earth seemed enormous. It stretched beyond sight, beyond imagination, its horizons forming a quiet illusion that the world was infinite, stable, and central to all things. Mountains rose like immovable walls. Oceans appeared boundless. The sky turned above ancient civilizations with a dependable rhythm, suggesting a universe shaped around the ground beneath their feet. Yet in the slow turning of the ancient world, a few minds began to suspect that this vastness was only a matter of perspective, that Earth's size was not what it seemed, and that to measure it was to challenge humanity's oldest assumptions. Long before telescopes and satellites, in an age when the sun was still worshipped as a god, a Greek scholar named Eratosthenes attempted something extraordinary. In 240 BCE, he stood in the intellectual heart of Alexandria, surrounded by scrolls, maps, and the restless curiosity of a library that sheltered the knowledge of entire civilizations. He had heard reports that at noon on the summer solstice in the city of Syene, the sun cast no shadow, that its light fell straight into a deep well, illuminating water at the bottom. In Alexandria, however, shadows still stretched along the ground at the same moment. To most, this was a trivial observation. But to Eratosthenes, it was the whisper of a curve, the first hint that Earth's surface bent gently beneath his feet. By comparing the angle of a shadow in Alexandria to the absence of one in Syene, he calculated the circumference of the Earth with a precision astonishing even by modern standards. Without rockets, lasers, or orbital sensors, he measured the size of the planet using only sunlight, geometry, and the belief that nature followed patterns waiting to be revealed. This was the first time humanity gave Earth a number, a measurement, a boundary, an identity. Yet while Eratosthenes was calculating with shadows, other civilizations were reading the sky. In Babylon, clay tablets were etched with star lists and celestial cycles, mapping the movements of planets long before their true nature was understood. The Babylonians could not yet say how large the Earth was, but they recognized that its patterns were intertwined with those of the heavens, that the sky above was a kind of cosmic clock, turning with a precision that hinted at deeper structure. A few centuries later, the scholars of Alexandria refined these observations. They charted stars with increasing accuracy, built instruments that could measure angles smaller than a fingernail's width, and began imagining a universe far larger than the myths that had shaped early civilizations. The Earth, they realized, did not command the heavens. It participated in them. Far to the south and east, in the Islamic Golden Age, observatories rose from the sands, grand geometric structures dedicated to the sky's quiet order. Places like Baghdad, Moraga, and Samarkand became centers of astronomical refinement. Scholars such as Al-Biruni attempted new measurements of Earth's radius by observing the angle between the horizon and the summit of a mountain, using trigonometry to estimate the planet's curvature. Others, like Ibn al-Shatter, produced planetary models whose mathematical precision later echoed in the work of European astronomy. These observatories, equipped with sextants towering several stories high, became humanity's early gateways to cosmic scale. They did not yet know the true size of the sun or the distance to the stars, but they grasped something essential: Earth was measurable. Not infinite, not central, and not immune to the laws shaping the wider universe. Then came a moment that fractured the ancient illusion completely. In the 16th century, Nicholas Copernicus proposed a model that shifted Earth from the sacred center to a single point among several wandering planets. His heliocentric vision was not just a rearrangement of orbits. It was a philosophical tremor. For millennia, Earth had been the stage on which the cosmos performed. Now it became one actor among many, neither the largest nor the most significant. With this, Earth suddenly shrank in meaning as much as in proportion. A few decades later, Galileo Galilei lifted a telescope toward the sky, transforming human perception with a simple tube of glass. He observed mountains on the moon, proving that other worlds were rugged and real. He discovered moons orbiting Jupiter, revealing that not all motion centered on Earth. He saw sunspots drifting across the sun's surface, marking it not as a perfect divine sphere, but as a turbulent star. Each discovery chipped away at Earth's former grandeur. The planet was solid, limited, and bound to the same physical laws that governed distant worlds. Slowly, humanity learned to look upward with new eyes. The question was no longer what Earth was, but where it belonged, and how its size compared to the immense structures surrounding it. As the first detailed star charts emerged, as navigation required accurate latitude and longitude, as instruments like the astrolabe and quadrant became essential tools, the relationship between Earth and the cosmos became clear. The planet could be mapped. Its curvature could be plotted. Its diameter could be estimated. All of these were measurable quantities, definable and finite. Across cultures and centuries, scholars who never met, separated by language, geography, and belief, contributed to a single unfolding realization: Earth was not the universe, it was an object within it. This shift marked the beginning of cosmic scale. Once the planet had a size, humanity naturally reached toward the next question: how large was the sun? How far were the stars? How wide was the sky itself? By the 17th century, with the works of Johannes Kepler and Isaac Newton, the solar system became a structured machine. Distances between planets could be calculated, orbital periods predicted. Earth's measurements became part of a larger architecture. The solar system revealed itself not as a backdrop, but as a vast arena where Earth was one participant among many. Then, in the centuries that followed, the universe expanded again. Telescopes grew larger. Observations grew sharper. Light became a messenger that carried the scale of the cosmos across unimaginable distances. Humanity learned that stars were suns, that the Milky Way was a galaxy, and that the universe stretched far beyond its boundaries. Earth's size, once a monumental quantity, faded into a humble statistic. Yet this humbling did not diminish the planet. Instead, it revealed a truth that would guide the rest of scientific history. The meaning of size is defined by context. A mountain is large to a person. A continent is large to a mountain. A planet is large to a continent. And a star dwarfs a planet until both disappear in the glow of a galaxy that itself becomes a single point within the cosmic web. As soon as humanity measured Earth, it began to measure everything beyond it, and the story of cosmic scale unfolded. This chapter marks the threshold between ancient curiosity and modern understanding. It is the moment where Earth stops being the center and becomes the first stepping stone to cosmic perspective. Now the journey extends outward, toward the giants of the solar system, the furnace of the sun, the abyss between stars, and the spiraling architecture of the Milky Way. With every step, Earth changes its meaning, from enormous to small, from central to peripheral, from known to wondrously insignificant. And yet, In this shrinking, something profound emerges. By questioning Earth's size, humanity opened the door to the universe itself. There are moments in human history when a single idea fractures the world. Moments when the familiar becomes unsteady, when certainty dissolves, and when the quiet rhythm of daily life is interrupted by a realization so profound that it reshapes the mind itself. The story of Earth's true scale begins not with measurement, but with shock. The shock of discovering that the planet is not what it once seemed. For thousands of years, the Earth had occupied a special place in human imagination. It was the unmoving foundation of existence, the steady platform on which the cosmos revolved. Everything, the sun, the moon, the wandering planets, appeared to circle it with obedient precision. This vision of a centered world was not merely scientific. It was emotional, cultural, and spiritual. It offered a feeling of importance, a sense that humanity stood at the cosmic center. But then, in the quiet halls of Renaissance Europe, a Polish astronomer named Nicholas Copernicus gathered the courage to suggest something unthinkable. The Earth, he proposed, was not the center of anything. It was a world in motion, circling the sun like every other planet. His heliocentric model did not simply rearrange celestial bodies. It dethroned humanity from the heart of the universe. The shock was immediate and immense. Copernicus did not live to see the full storm his ideas would unleash. He died the same year his great work, De Revolutionibus Orbium Coelestium, was published. But his theory drifted through Europe like a quiet explosion. Suddenly, Earth was no longer fixed. It was a traveler, a wanderer, a small, moving point in a cosmic sea. The size of the planet had not changed, but its meaning had, and meaning, for humanity, often matters more than measurement. Then came a moment that would strip away the last illusion of Earth's uniqueness. In 1609, Galileo Galilei raised a telescope, a simple, fragile instrument, barely strong enough to magnify the heavens, and aimed it toward the moon. What he found destroyed a belief older than civilization itself. The moon was not a smooth, perfect orb. It was scarred with valleys and crowned with mountains. Light spilled across its rugged terrain like dawn over an alien world. Earth, then, was not singular. It was not superior. It was one world among many, sharing the same rough geology, the same imperfections. And if the moon had mountains, then the heavens were not realms of divine perfection. They were landscapes. Places. Real and reachable. Galileo's telescope turned Earth from the universe's exception into one of its participants. Soon, Galileo pointed his lens toward Jupiter and witnessed 4 small moons orbiting the giant planet. These tiny points of light, Io, Europa, Ganymede, and Callisto, circled their world with a precision that echoed Earth's own movements around the sun. Their existence was an irrefutable sign that the cosmos did not revolve around a single center. Motion was everywhere. Gravity worked on every scale. The universe was a system, not a hierarchy. And with that, Earth became small. The shrinking did not end there. Johannes Kepler, working with meticulous data collected by Tycho Brahe, uncovered a truth that expanded the solar system beyond anything previously imagined. Planets did not move in perfect circles. They followed long, sweeping ellipses, paths so vast that Earth's circumference was trivial in comparison. Mars alone traveled an orbit that, if stretched into a straight line, would dwarf the entire size of Earth tens of thousands of times. The solar system, once imagined as a tight, orderly arrangement of nested spheres, suddenly ballooned into immensity. Earth's orbit alone formed a circle about 300 million kilometers across, a scale so large that human intuition faltered before it. The planet itself became a speck tracing a wide ring around a star that was itself only one among billions. The emotional impact was as striking as the scientific one. Humanity had lost not only its cosmic location, but its sense of scale. Earth was no longer the measure of all things. It was something to be measured against far greater structures. For some, this brought a sense of humility. For others, a quiet existential fear. If Earth was small, what did that make humanity? Fragile creatures standing on a minor planet orbiting an ordinary star in a universe that did not acknowledge their existence. And then, centuries later, the universe fractured again, this time in a way that redefined the concept of size itself. In the early 20th century, Albert Einstein published his theory of general relativity, a work that did not simply describe gravity, but rewrote the architecture of reality. According to Einstein, space and time were not empty backgrounds. They were dynamic entities, bending and stretching under the influence of mass and energy. Suddenly, distance was not absolute. Scale was not fixed. Gravity was geometry. Space curved around massive objects. Time stretched near strong gravitational fields. The universe was not a rigid box but a flexible fabric, capable of warping under the weight of stars, galaxies, and clusters. Under relativity, Earth's size became even harder to define. Its physical diameter remained the same, but its place in space depended on the invisible curvature sculpted by the Sun's mass. Its orbit was not a perfect ellipse, but a path carved by the bending of spacetime. Even light, the fastest and most constant traveler, could be deflected, stretched, and slowed by gravity's influence. Einstein showed that the true scale of the universe was a moving target, shifting with perspective, velocity, and gravitational depth. A meter on Earth was not the same as a meter in orbit. A second near the Sun was not the same as a second in open space. Reality itself expanded and contracted according to conditions that human senses could not perceive. This revelation shattered the last remnants of the ancient worldview. Earth was not only small, it existed within a universe that refused to remain still long enough to measure it. At cosmic scales, planets became approximations, stars became statistical averages, and galaxies stretched like fabric in an expanding space. The emotional shock of this realization echoed the early tremors of the Copernican revolution. Humanity once again found itself displaced, not just from the center of space, but from the center of understanding. The world beneath human feet was not the foundation of the cosmos. It was a tiny ripple in an ever-changing sea of spacetime. From Galileo's mountains on the moon to Einstein's curvature of reality, each discovery chipped away at Earth's primacy. What remained was a truth both unsettling and liberating. The planet was not the measure of the universe. It was an island, small, fragile, and profoundly beautiful, floating in a cosmos whose scale defied all intuition. Earth had become small. But in its smallness, a new kind of significance emerged, not as a cosmic center, but as a rare world where life could contemplate the immensity beyond it. And so the story continues, for the shrinking of Earth was only the beginning. The next chapters would reveal that even the solar system, the galaxy, and the universe itself hold scales that make Earth's size vanish into a whisper. A gentle reminder that to understand the cosmos is to embrace both awe and insignificance in equal measure. In the long arithmetic of the cosmos, measurement becomes a form of humility. The deeper astronomers looked into the solar system, the more the Earth seemed to fold inward, shrinking against a landscape of magnitudes that defied ordinary sense. Here, across these vast celestial distances, scale is not merely a number, it is a quiet revelation, a widening of perspective that reshapes the meaning of home. The comparison began with what was closest. The Moon, Earth's silent companion, orbits at a distance of roughly 384,000 kilometers, a span so large it could hold every continent end to end with oceans still in between. Yet the Moon itself is only a quarter the width of Earth, scarred and airless, lacking the layers of atmosphere and liquid oceans that cradle life. Through spacecraft measurements and laser ranging experiments left by Apollo astronauts, scientists mapped its precise mass, radius, and gravity. The lunar world became Earth's first mirror, showing the fragility and uniqueness of its own blue surface. Against the deep black of space, Earth already seemed small, but beside the Moon, it still held the confidence of a planet that believed it was large. That confidence faded as the comparison widened. Mars, only slightly over half Earth's diameter, revealed deserts older than any terrestrial rock and volcanoes that dwarfed the Himalayas. Olympus Mons, rising more than 21 kilometers above the Martian plains, stood 3 times taller than Mount Everest. Through orbiters like Mars Global Surveyor and landers that pressed their instruments into the rust-red soil, scientists uncovered a world both familiar and alien, a frozen desert with the memory of seas, a planet seemingly sculpted on a scale meant to challenge Earth's proportions. Venus, almost Earth's twin in size, exceeded it radically in temperature and atmospheric density. Crushed beneath a pressure 90 times that of Earth's surface and heated to nearly 460 degrees Celsius, Venus demonstrated that even planets of similar dimensions could inhabit entirely different realms of possibility. In the solar system's unfolding map, Earth began to lose its sense of being a standard. It became merely one sample among many. Then the comparisons reached Jupiter, and Earth's scale collapsed entirely. Measured through the precise instruments of Voyager, Pioneer, Cassini, and later Juno, Jupiter emerged as a world of impossible dimensions. 11 Earths laid side by side could stretch from one edge of the gas giant to the other. More than 1,300 Earths could fit inside its swollen volume. Its great red spot, a storm larger than the entire surface area of Earth, had been churning for centuries, perhaps millennia, with winds that roared beyond comprehension. Even Jupiter's faint rings and numerous moons formed a miniature system of their own, a reminder that Earth was not even the grandest world in its neighborhood. Saturn continued the humbling lesson. Far beyond its iconic rings, thin and delicate, composed of ice shards tracked by Cassini with exquisite precision, lay a planet nearly as large as Jupiter but dramatically less dense, capable of floating on water if such a thing were imaginable. Its rings stretched more than 280,000 kilometers from rim to rim, wide enough to hold nearly 3/4 of the distance between Earth and the Moon. Against these silent colossi, Earth appeared almost invisible, a fragile sphere of oceans and continents dwarfed by giants sculpted from hydrogen and helium. But the true diminishment came when scientists compared Earth not to planets, but to the star that held them all in orbit. The Sun, a sphere of nuclear fire, stood as a monument to incomprehensible scale. Precise measurements, sharpened by spacecraft like SOHO and Stereo, revealed that the Sun's diameter reached 1.39 million kilometers, wide enough to line up 109 Earths across its glowing face. In volume, the Sun could swallow more than 1 million Earths. Its energy output, fueled by hydrogen fusion at its core, radiated into space with a consistency that shaped the very conditions for life on a single tiny world circling 150 million kilometers away. Here, Earth shrank again. No longer a globe, but a point of color drifting in an ocean of radiation and light. Even the space that Earth traveled through became a measure of its smallness. Its orbit, spanning 300 million kilometers in circumference, seemed immense until compared with the wider paths of its neighbors. Mercury traced a tight, rapid ellipse close to the Sun, while Neptune drifted so far away that sunlight took 4 hours to reach it. Earth's orbit was only one thread in a tapestry that stretched outward into colder, darker territory, each planetary path expanding the scale by factors that multiplied almost without end. Voyager and Pioneer pushed these limits further. As they drifted past Jupiter, Saturn, Uranus, and Neptune, their instruments returned numbers that reorganized the solar system in human understanding. Distances once imagined as abstract grew exact. The void between planets became a measurable expanse. Saturn's rings were mapped down to features only a few hundred meters wide. Jupiter's magnetic field was charted with fidelity. Neptune's winds were recorded at more than 2,000 kilometers per hour. Each detail enlarged the solar system, and Earth shrank with every revelation, an island in a sea that grew deeper the more it was explored. Cassini, orbiting Saturn for more than a decade, carried the next wave of precision. It measured Titan's methane-rich lakes, the icy geysers erupting from Enceladus, and the gravitational harmonies of Saturn's rings. These measurements defined scales so vast and varied that Earth no longer seemed like the baseline for comparison but rather a single example within a sprawling family of worlds. Juno then arrived at Jupiter, locked in a polar orbit that revealed the planet's swirling atmosphere, metallic hydrogen core, and deep, rotating storms. Its data sharpened the distinctions between Earth and Jupiter to an extent never before possible. The gas giant's gravity field alone dwarfed anything Earth could produce. The precision of Juno's readings transformed Jupiter from a distant spectacle into a deeply quantified giant, and Earth, when measured against it, became smaller not by metaphor, but by mathematics. But even these planetary comparisons paled before the broader boundary of the solar system itself. Beyond Neptune, past the scattered ice of the Kuiper Belt, lay a frontier that defined the outermost breadth of the Sun's influence, the heliosphere. Voyager 1 and Voyager 2, launched in 1977, eventually crossed this boundary, a region where the solar wind finally surrendered to the interstellar medium. Their instruments marked the transition not through visuals, but through shifts in particle density, magnetic field direction, and the thinning hum of solar plasma. The heliosphere, swollen by the Sun's constant exhalation, extends more than 120 astronomical units from the star, a bubble more than 20 billion kilometers wide. Against that vast enclosure, Earth's orbit, only 1 astronomical unit from the Sun, seemed like a tiny ring drawn close to a torch flame. But even the heliosphere was not the final measure of scale. Far beyond it, surrounding the entire solar system, stretched a theoretical sphere of icy debris, the Oort cloud. Though never directly observed, its existence is inferred from the trajectories of long-period comets, bodies that sweep into the inner solar system from distances where sunlight is little more than a memory. The Oort cloud may extend nearly 100,000 astronomical units from the Sun, a boundary nearly 100,000 times wider than Earth's orbit. If the solar system were reduced to the size of a room, Earth would be a speck of dust near a lamp, and the outer edge of the Oort cloud would lie nearly 100 kilometers away. Here, Earth shrank not simply in size, but in significance. The tiny blue sphere that once seemed enormous now floated inside a structure so immense that human language faltered at describing it. Distances ceased to behave like ordinary measurements. They stretched into abstractions, reminders of how small any single world could be. Yet the shrinking of Earth brought not despair, but clarity. It became evidence of a truth that both Voyager spacecraft now silently carry with them into interstellar space, that meaning does not depend on size. Earth's smallness became a testament to its uniqueness, its improbable balance of gravity, warmth, water, and atmosphere. In the vast arena of the solar system, Earth did not need to be large to be extraordinary. It only needed to be alive. Across the expanding frontier of knowledge, a moment arrives when scale loosens from familiar numbers and enters a realm where comparison becomes an act of surrender. The solar system, vast though it seemed, remained intimate, a neighborhood mapped by probes, warmed by a single star, and bounded by forces still traceable to the Sun's distant breath. But beyond that boundary lay the interstellar expanse, a territory so wide and so empty that Earth's size dissolved into something smaller than a whisper. This was where insignificance was first truly measured. The journey outward began with the closest star. Proxima Centauri, a red dwarf only 4.24 light-years away, sat in space like a smoldering ember, small, dim, and ancient. Its radius was barely 1/7 that of the Sun, and its light reached farther through stellar storms than steady radiance. Yet in distance alone, Proxima represented a chasm beyond human scale. More than 40 trillion kilometers of near-absolute darkness separated it from Earth. The vacuum between these two stars was so complete that a spacecraft traveling faster than any probe ever launched would take tens of thousands of years to bridge it. Already, Earth's dimensions, measured in mere thousands of kilometers, slipped into irrelevance. Compared to the gulf between stars, the entire planet became a mote suspended in a vast and unbroken night. Nearby, Alpha Centauri A and B formed a binary pair whose orbits intertwined in cycles lasting decades. These two suns radiated with a brightness and size more reminiscent of the Sun than of Proxima. Alpha Centauri A, slightly larger and hotter than the Sun, carried the mass to sculpt space around it with a gravitational field extending billions of kilometers in all directions. Yet even these stars, measured against Earth, revealed a disparity too great for proportion. Over 1 million Earths could rest inside Alpha Centauri A. Its light, its heat, its pressure, all operated on scales that turned Earth into a chemical anomaly on the edge of a cosmic furnace. Still, the comparison had barely begun. Far beyond the Centauri system burned Betelgeuse, a red supergiant swollen by the late stages of stellar evolution. Its outer layers were so expanded and diffuse that if Betelgeuse were placed at the center of the solar system, its fiery surface would engulf Mercury, Venus, Earth, and possibly stretch beyond the orbit of Mars. Telescopes captured its shifting face, its convective cells rising and collapsing like continents of fire. Betelgeuse did not simply dwarf Earth. It erased it, consuming the scale of entire planetary systems in a single sphere of luminous gas. Then came the Leviathans. VY Canis Majoris, one of the largest known stars, defied all terrestrial intuition. With a radius over 1,000 times that of the Sun, it described a boundary so vast that Earth's orbit around the Sun could fit comfortably inside its swollen atmosphere. The size of this star required scientific notation merely to express it. Imagining Earth beside VY Canis Majoris was no longer comparison but abstraction. The planet became a fraction of a fraction, a point so small that dividing it further served no purpose. And yet even VY Canis Majoris did not mark the upper limit of stellar magnitude. Stephenson 2-18, discovered within a dense cluster of red supergiants, emerged as one of the largest stars ever observed. Its estimated radius exceeded 2,000 times that of the Sun. If placed where the Sun now burned, Stephenson 2-18 would stretch beyond the orbit of Saturn, wrapping Earth's orbit deep within its incandescent envelope. The human mind, accustomed to mountains, oceans, and landscapes, found little to anchor itself to in such dimensions. Earth was now too small for analogy, too small for metaphor, too small even for scale. It had become unmeasurable in practical terms. Between these titanic stars lay distances that multiplied the insignificance even further. The space separating them was not crowded with objects or debris but filled instead with almost perfect emptiness. Trillions of kilometers of cold, silent vacuum extended in every direction. Photons wandered for years before meeting another surface. Dust grains, separated by entire planetary distances, drifted like cosmic exiles. In this domain, Earth's 12,742-kilometer diameter could not be meaningfully plotted. Even the solar system, spanning billions of kilometers, became a thin line when mapped against the interstellar dark. For the first time, Earth was not merely small. It was effectively invisible. Scientists, attempting to express these distances, turned to light years and parsecs, but even these units served only as temporary scaffolding. Light, traveling at 300,000 kilometers per second, would need over 4 years to reach Proxima Centauri, and nearly 8 to reach the broader Centauri system. Betelgeuse lay more than 500 light-years away, while Stephenson 2-18 resided deep within a cluster thousands of light-years from Earth. The scale of the interstellar medium had stretched so far beyond planetary dimensions that Earth became lost in numbers that no longer referenced anything human. Yet the realization still had further to go. Beyond individual stars unfolded the architecture of the Milky Way itself, a barred spiral galaxy with a diameter of roughly 100,000 light-years. Along its arms drifted hundreds of billions of stars, each accompanied by gravitational fields, planets, debris belts, and distant clouds of frozen material. The most advanced attempts to compare Earth with this structure bordered on symbolic rather than numerical. The Earth was not a needle in a haystack, it was a molecule compared to a mountain. Even that description exaggerated its size. If the Milky Way were reduced to a map the size of a continent, Earth would vanish. Its orbit, its atmosphere, its oceans, everything familiar, would fall below the resolution of the smallest grain of sand. The planet's physical presence could no longer be drawn meaningfully at any scale large enough to display the galaxy. It was not simply small, it was beneath the threshold where its dimensions mattered at all. Here, insignificance reached its first true form. Astronomers studying these vast proportions often describe the interstellar void as the moment where human intuition failed. For distances within the solar system, models could shrink planets and orbits into manageable diagrams. But between stars, the ratios collapsed. Earth's diameter, when divided against a light year, produced numbers so tiny that they bordered on the infinitesimal, values with decimal places stretching outward like numerical echoes. This was the point where measurement itself became philosophical. Earth, once imagined as the center of creation, had now fallen below the scale of stellar comparison. Against Proxima Centauri, it was negligible. Against Betelgeuse, it disappeared entirely. Against Stephenson 2-18, it became mathematically irrelevant. And against the Milky Way, a spinning cathedral of gas, dust, and gravitational motion, Earth could no longer be meaningfully plotted. Yet the insignificance carried a paradox. The same emptiness that diminished Earth also revealed how precious it was. In a galaxy where most planets were silent, frozen, or scorched, Earth held a fragile chemistry tuned to narrow boundaries of temperature, pressure, and light. Its thin film of atmosphere sheltered oceans that persisted for billions of years. Its surface produced forests, continents, weather, seasons, and life, something no comparison of sizes could devalue. Insignificance, then, was not a verdict but a vantage point. It marked the moment when Earth shed the illusion of cosmic importance, descending into its true scale. The journey from solar system to interstellar space revealed distances so vast that numbers ceased to describe them. And in this new perspective, where stars dwarfed planets, where voids stretched across light years, where galaxies spanned horizons of unimaginable breadth, Earth's smallness became the first quiet truth of the universe. A truth that, in its humility, allowed the next questions to form. Across the quiet reaches of the night sky, the Milky Way stretches like a pale river of stars, a soft band of light that seems delicate from the ground. But behind that faint glow lies an architecture so vast, so layered, and so ancient that any attempt to place Earth within it becomes an exercise in letting go of scale itself. What appears gentle to the human eye is, in truth, a rotating metropolis of hundreds of billions of suns, dust clouds the size of star systems, and gravitational structures that have survived since the infancy of the cosmos. And within this enormous design, Earth drifts in a position so modest that it struggles to be meaningfully defined. The Milky Way is a barred spiral galaxy, a great cosmic wheel measuring around 100,000 light-years across. Its core forms a bulge of tightly packed stars, many older than the solar system itself. Surrounding this luminous heart, a central bar of hot, young stars stretches outward like a glowing spine, twisting into sweeping spiral arms that curve gracefully through space. These arms are not solid structures but patterns of density, regions where gas clouds compress, collapse, and ignite into new suns, leaving trails of starlight that spiral outward into the dark. Yet the visible part of the galaxy is only a small fraction of its full anatomy. Enveloping the Milky Way lies the galactic halo, a roughly spherical cloud of ancient stars, diffuse gas, and clusters that orbit at great distances from the disk. Beyond that, extending even farther, is an invisible structure known as the dark matter halo, a gravitational scaffold that outweighs all the galaxy's luminous material combined. It is this hidden web of unseen mass that holds the Milky Way together, preventing its rapid rotation from tearing it apart. Without dark matter, every star would drift into intergalactic space, dissolving the galaxy like mist dispersed by wind. Somewhere between these structures lies Earth, tucked inside a minor fragment of a spiral arm known as the Orion Spur. The Orion Spur is not one of the major arms that define the Milky Way's elegant form. It is a small, local bridge between the Sagittarius and Perseus arms, a modest interstellar shelf of stars and dust. Earth sits roughly 27,000 light-years from the galactic center, orbiting in a calm and unremarkable region far from the violent stellar nurseries and destructive black hole tides that shape the inner galaxy. This location, quiet and peripheral, has allowed life to endure without interruption from supernovae, gamma-ray bursts, or the gravitational upheavals that dominate the central bulge. Yet this very safety comes at a conceptual cost. At this distance, Earth becomes almost invisible. The human planet, with a diameter measured in mere thousands of kilometers, cannot be plotted on any scale that fits the spiral structure of the galaxy. Even the solar system, nearly 287 billion kilometers wide when including the outer Oort cloud, collapses into a single pixel when overlaid on a galactic map. And then comes the central question: what becomes of Earth when compared to the objects that anchor the Milky Way? At the galaxy's center lies Sagittarius A*, a supermassive black hole weighing about 4 million times the mass of the Sun. Though its event horizon spans only a fraction of the solar system, its gravitational influence governs the motion of stars thousands of light-years away. Earth, in comparison, is smaller than any meaningful measure near this cosmic engine. It is not merely tiny, it is absent. No diagram of Sagittarius A** can include Earth size without violating the limits of graphical representation. The planet becomes not a dot, not a point, but an abstraction far below the threshold of visibility. And the galaxy itself dwarfs its central anchor. The Milky Way's disk stretches roughly 100,000 light-years across and about 1,000 light-years thick at the Sun's location. This vast disk rotates like a colossal wheel, and Earth, along with the entire solar system, races around the center at approximately 220 kilometers per second. At this speed, the planet traverses the distance of a continent every second, yet it still requires about 230 million years to complete a single orbit around the galactic center. In that span, mountains rise and erode, species emerge and vanish, continents drift and collide, and oceans reshape the face of the Earth. One galactic year outlives civilizations, languages, and epics. Earth has traveled more than 18 times around the galaxy since life first blossomed on its surface. But speed does not grant significance. In the context of this massive rotating disk, Earth's size falls beyond practical depiction. To place the planet on a map of the Milky Way would be like trying to draw a single atom on a world map of the Pacific Ocean. The atmosphere becomes unmeasurable. The oceans become unmeasurable. The crust and mantle and core become unmeasurable. The entire planet becomes smaller than mathematical rounding error. And even that scale is soon exceeded. Encircling the Milky Way's visible structure lies the dark matter halo, an invisible sphere estimated to be more than 1 million light-years across. This halo is not a distant shell but a gravitational field traced through the motion of stars and gas clouds. It shapes the galaxy, defines its boundaries, and forms the gravitational well in which the solar system drifts like a particle of dust carried by deep ocean currents. Against this invisible sphere, Earth disappears again. The entire galaxy becomes the relevant unit of measurement, and everything smaller than a star system collapses into nothingness. In the mathematics of galactic motion, Earth is not simply tiny, it is omitted. Its mass is too trivial, its diameter too small, its orbit too narrow. It becomes a value so slight that removing it from the equations changes nothing at all. Yet even the Milky Way is not the final scale. Across the cosmic void, galaxies gather into clusters bound by gravity, drifting through the universe in vast swarms. The Milky Way belongs to the Local Group, a collection of more than 50 galaxies, including the Andromeda Galaxy and the Triangulum Galaxy. And beyond the Local Group lies the Laniakea supercluster, a gravitational basin containing over 100,000 galaxies. Its structure stretches across 500 million light-years, forming rivers and filaments of galaxies that flow toward the Great Attractor, a mysterious region of space whose gravity bends the motions of galaxies across hundreds of millions of light-years. Here, the cosmic web reveals itself for the first time. Clusters form knots in a filamentary lattice of dark matter and luminous matter. Galaxies trace the strands of this structure like beads strung along invisible threads. And between these filaments lie the great voids, enormous expanses with almost no galaxies, some measuring hundreds of millions of light-years across. At this scale, even the Milky Way appears fragile, a single glowing island floating in a sea too vast to comprehend. Earth, by contrast, ceases to exist in any meaningful sense of scale. It becomes a quantity so small that enlarging it enough to be visible would shrink the cosmic web to a blur. It becomes irrelevant not through absence, but through disproportion. No diagram of a galaxy cluster can include a planet. No map of the cosmic web can admit a star system. Earth vanishes entirely, not erased, but dissolved into the mathematics of negligible contribution. And yet, Amid this dissolution, a deeper mystery emerges. The structures that render Earth invisible also made Earth possible. The galaxy's quiet outskirts shielded the solar system from destructive radiation. The spiral arms provided the heavy elements needed for life. The dark matter halo held the galaxy together long enough for planets to form, oceans to settle, and biology to awaken. The cosmic web's rivers of matter shaped the Milky Way in the first place, guiding its birth from primordial clouds after the Big Bang. In the end, Earth disappears from the scales that measure galaxies, clusters, and superclusters, but it remains present in a far more profound way. It is a world small enough to vanish from view, yet complex enough to question the structures that dwarf it. The mystery of its insignificance only deepens. In the quiet mathematics of the cosmos, size is not merely a measurement. It is a shifting language, a negotiation between matter, energy, and the restless fabric of spacetime. And as the universe grows older, this language grows stranger, more fluid, more difficult to anchor to anything familiar. For more than a century, scientists have tried to understand how the universe determines scale. Their search begins with a difficult truth. In a cosmos that expands, stretches, curves, and ripples, size is not absolute. It is conditional, a property that depends on the laws that sculpt the universe itself. The first of these laws came from a quiet patent clerk in 1905. Einstein's theory of special relativity dismantled the idea of fixed lengths and frozen clocks. It revealed a universe where motion bends measurement, where distances contract for the fast-moving, and where time itself folds inward, refusing to behave uniformly. But Einstein was not finished. 10 years later, he extended the idea into something vaster and more unsettling: general relativity, a theory in which gravity is not a force, but the shape of space-time itself. In this geometry, space curves around mass, time slows near energy, and distance becomes a flexible quantity that shifts with the landscape. In such a universe, defining size becomes a deeper challenge. For even a simple line, the separation between two stars, can lengthen or shrink depending on the curvature of the cosmic stage beneath it. Yet the universe complicates the question further, because space is not only curved, it is expanding. This revelation arrived in the early 20th century, when Edwin Hubble observed distant galaxies drifting away from one another. Their light was stretched toward the red, not because they moved through space, but because space itself was growing, pulling galaxies apart like points drawn on an inflating sphere. In this expanding universe, distances are no longer fixed markers. They evolve. A galaxy today is farther than it was yesterday, not because it traveled there, but because the universe expanded between here and there. This kind of distance, a dynamic, evolving separation, is unlike anything found on Earth. And it reshapes what size even means. At the largest scales, this expansion is ruled by something even more mysterious: the cosmological constant, or dark energy, a pressure embedded in the vacuum of space. It accelerates the expansion, adding new distances between galaxies, stretching the cosmic fabric faster with every passing moment. Under its influence, the universe behaves like a vast tide that never reverses, always rising, always widening. And in its relentless pull, the idea of size becomes slippery. A galaxy cluster may be gravitationally bound and stable, but the universe around it continues to widen. A supercluster may appear colossal, but even it is dwarfed by the swelling cosmic sea. In an expanding universe, size becomes a story of competing forces: gravity binding matter inward, and dark energy pushing space outward. What we call large exists only in the tension between these two cosmic impulses. But to understand how strange this becomes, the journey must go back to the beginning, to a moment before galaxies, before atoms, before even the laws of physics had settled into their final form. In the earliest fractions of a second, the universe underwent a phenomenon known as cosmic inflation, a burst of exponential expansion so violent and so brief that it remains one of the most extreme events in cosmic history. In less than a heartbeat, space-time ballooned by unimaginable factors, smoothing the universe and stretching quantum fluctuations into the seeds of galaxies. This violent swelling raises a profound question. If space can expand faster than light, if distance can grow without limit, then what does size truly measure? A position? A boundary? A momentary shape of something that is always shifting? Cosmic inflation does not merely describe what happened. It hints at what might still be happening. Many theorists propose that inflation never fully ended, that it continues in remote regions, spawning countless universes like bubbles in a boiling cosmic ocean. In this concept of eternal inflation, scale becomes an infinite hierarchy. Our observable universe becomes one pocket among untold others, each with its own geometry, its own laws, and its own definition of size. And if this hierarchy exists, then Earth's scale is not only small, it becomes undefinable, lost in an endless branching of cosmic domains. Other theories push the question further. Higher dimensional models, such as those in string theory, propose that the universe may contain extra dimensions curled into spaces too small for humans to imagine, compact loops of geometry that exist within every point of ordinary space. These dimensions redefine what small means. A particle may be point-like in 3 dimensions but extended or looped in 9 or 10. In such a universe, Earth's familiar scale is only a surface view, a thin cross-section of something more intricate and hidden. Still, other ideas challenge the meaning of space itself. The holographic principle proposes that the entire 3-dimensional universe may be encoded on a 2-dimensional cosmic boundary, like a vast projection of information written on the edge of space-time. If true, then size is an emergent illusion, a product of information density rather than spatial extent. In this holographic universe, Earth's size is not measured in kilometers or volume, but in the number of bits required to describe its existence. But even as theories expand outward into the infinite, another frontier lies at the opposite extreme, the limit of the very small. In the quantum domain, distances cannot shrink forever. There is a frontier known as the Planck length, the shortest unit where the known laws of physics still make sense. At this scale, 1/10 million trillion trillionth of a meter, space-time becomes turbulent and undefined. The smooth geometry of relativity dissolves into quantum foam, a storm of fluctuating shapes, fleeting wormholes, and restless energy. Below this scale, measurement itself loses meaning. There is no smaller size. Not because something prevents it, but because the concept itself collapses. This lower limit, paired with the infinite expansion of the upper limit, reveals a universe where size is a fragile construct, useful at human scales, but incomplete at cosmic ones. And this brings the story back to a quiet, almost philosophical question. Does Earth's size have meaning in a universe where space stretches, where boundaries shift, where measurement itself appears to be an emergent property of geometry? In the cosmic hierarchy, Earth occupies a thin band of scale, far above the quantum foam, far below the cosmic web. It exists in a middle world, where size is still stable, still measurable, still familiar. But the universe around it does not share this stability. Its expansion has no center, no boundary, no fixed frame against which size can be judged. And beyond the observable horizon, distances expand faster than light, separating regions forever. In such a universe, Earth's size becomes a local truth, meaningful within the solar system, but fading into irrelevance beyond it. Galaxies drift apart. Clusters stretch with the void. Superclusters loosen their gravitational bonds. And in the quiet widening of the cosmic field, the idea of size dissolves into motion, curvature, and expansion. The mystery deepens because the universe does not offer a single definition. Size can be a distance, or a geometry, or an information content, or a dimension among many. And in this shifting landscape, Earth becomes something even smaller than small. Not a grain, but an object whose scale is meaningful only within the fragile island of spacetime it calls home. The universe is vast. Its laws are fluid, and its definition of size may always remain beyond the reach of any world, especially one as small, as temporary, as fleeting as Earth. In a universe where distance stretches, where space curves, and where size itself flickers between certainty and doubt, measurement becomes humanity's quiet rebellion. Across deserts, mountaintops, and the cold vacuum beyond Earth's sky. A network of instruments stands watch, each one built to answer a single question. How large is the universe, and how can anything be measured within it? For more than a century, astronomers have extended their reach not by stepping farther, but by crafting finer tools, machines capable of intercepting faint whispers of light, subtle distortions in gravity, and the trembling motion of stars. The first of these modern sentinels sits in low Earth orbit, circling the planet every 97 minutes. The Hubble Space Telescope, launched in 1990, became the instrument that reshaped humanity's sense of scale. Its polished mirrors and sensitive detectors reached beyond atmospheric distortion, revealing a universe filled with galaxies stretching into deep time. Hubble measured the expansion of the cosmos, caught the glow of ancient stars, and traced the size of the observable universe with unprecedented precision. Its images did more than document distant structures. They sharpened the cosmic ruler itself. But as the universe grows older, its earliest light grows fainter. For that task, another instrument stands ready, a gold-mirrored eye placed 1 million miles from Earth. The James Webb Space Telescope observes in infrared wavelengths, peering through cosmic dust and looking back toward the primordial glow just after the Big Bang. Webb's measurements refine the distances to early galaxies, recalibrate cosmic expansion, and challenge assumptions about how quickly structures formed. Its sensitivity reveals galaxies so young and so bright that astronomers are forced to reconsider cosmic timelines, reminding humanity that each new measurement changes the scale it tries to define. Orbiting closer to home, the Gaia Observatory performs a different kind of work, not imaging faraway epochs, but mapping the immediate cosmic neighborhood with exquisite accuracy. Gaia tracks the subtle wobble of stars as Earth orbits the Sun, measuring parallax, the ancient technique that turns geometry itself into a cosmic yardstick. With this method, Gaia constructs a three-dimensional map of more than 1 billion stars, refining the Milky Way's shape and structure. For the first time in history, the galaxy is no longer an imagined spiral, but a measured and evolving object, a space defined by motion. Beyond Gaia's reach lies another set of instruments, created to detect the faint dimming of distant suns. Kepler and its successor tests search for planets by recording tiny reductions in starlight, shadows cast by worlds passing across their stars. Though built to find planets, these telescopes also measure scale indirectly. Every star they monitor becomes a marker in space, its position, brightness, and distance contributing to a broader cosmic map. And every planet they discover reminds humanity that measurement is not only about the vast, but also the intimate, that scale must stretch from the quantum to the universal. Further south, in the high desert of Chile, another tool stands in silence, a set of 66 antennas tuned not to visible light, but to radio waves. The Atacama Large Millimeter/Submillimeter Array, or ALMA, studies cold regions where stars are born. It captures the faint glow of molecules drifting in interstellar clouds, tracing the structure of galaxies at wavelengths invisible to the human eye. ALMA's precision reveals the motion of gas around black holes, the distribution of matter in distant galaxies, and the imprint of early cosmic structures. Each observation becomes another point on the universe's invisible measuring tape. Yet even these instruments capture only one side of scale. To understand the smallest dimensions, the thresholds where space-time begins to break apart, humanity uses tools far different from telescopes. Deep beneath the mountains of Switzerland and France, protons race through a circular tunnel at nearly the speed of light. The Large Hadron Collider, the world's most powerful particle accelerator, smashes them together to glimpse the fleeting patterns of the quantum world. In these collisions, physicists search for clues about the limits of matter, the structure of fields, and the shadows of particles that have yet to be found. Particle accelerators probe the opposite end of scale, the frontier where measurement dissolves into probabilities and uncertainty. But tools alone cannot measure the universe. They must be paired with methods, techniques that turn light, motion, and geometry into distances. One of the oldest of these methods is the standard candle, an object whose brightness is well understood. Type Ia supernovae serve as cosmic lighthouses. Their explosions shine with nearly identical intensity, allowing astronomers to infer their distance by how dim they appear. These supernovae revealed not only how far away galaxies lie, but also that the universe's expansion is accelerating, a discovery that introduced dark energy and reshaped the understanding of cosmic scale. Another tool is parallax, the simple but powerful shift in a star's apparent position as Earth moves around the Sun. Although ancient in concept, parallax has been transformed by Gaia into a high-precision instrument, yielding distances with accuracy once unimaginable. On still larger scales, astronomers turn to baryon acoustic oscillations, the faint imprint of primordial sound waves frozen into the large-scale structure of the universe. These ripples create a characteristic spacing between galaxies, a cosmic yardstick imprinted at the dawn of time. By measuring this separation today, astronomers track how the universe expanded across billions of years. Then there is gravitational lensing, a phenomenon predicted by general relativity. Massive objects warp spacetime, bending the path of light from more distant galaxies. By studying the distortions, astronomers map invisible matter, measure galaxy masses, and detect structures that emit no light at all. Lensing becomes both a magnifying glass and a measuring rod, turning gravity into a tool of scale. Together, these methods create a lattice of measurements, a scaffolding that stretches across the cosmos, linking the smallest quantum events to the largest cosmic structures. But this lattice is not yet complete. Many missions continue to refine it. The Dark Energy Survey, the Euclid mission, and NASA's upcoming Nancy Grace Roman Space Telescope all seek to determine the strength of dark energy, the rate of cosmic expansion, and the fine structure of the universe's geometry. Each mission tightens the uncertainties, adjusting the cosmic map with every observation. And each new result reveals that scale remains a moving target, a concept not yet fully resolved. Even now, a profound disagreement shadows modern cosmology, the Hubble tension. Two methods of measuring the universe's expansion produce values that do not match. Measurements made through the early universe, using the cosmic microwave background, yield a slower expansion rate. Observations of the nearby universe, using supernovae and Cepheid stars, give a faster one. This disagreement is not a nuisance, it is a clue. It suggests that the underlying assumptions about cosmic scale may be incomplete. Perhaps unknown particles shaped the early universe. Perhaps dark energy evolves with time. Perhaps space-time behaves differently on cosmic scales than current theories predict. In the tension between these measurements lies the future of cosmology. It is here, in the disagreement, that new physics may emerge. And so the instruments continue their vigil. Telescopes orbit above the atmosphere. Observatories listen from mountaintops. Particle accelerators probe the subatomic. Surveys map the galaxies. Each one extends the human reach a little farther. Each one tightens the definition of distance. Each one shapes the cosmic ruler that has no fixed length. For in a universe where the unmeasurable stretches on all sides, measurement becomes not an answer, but an ongoing act, a quiet declaration that even the vast can be traced, that even the shifting can be mapped, and that scale, though elusive, can still be pursued. In the quiet hours when telescopes turn toward the dark and instruments fall still, the universe expands not through measurement but through thought. What begins as a question of size slowly becomes something else, an invitation to reconsider the meaning of living on a world that is, by every astronomical measure, impossibly small. Across the cosmic scale, Earth is a whisper. It is smaller than the margin of a graph tracing the orbit of stars, smaller than the rounding error in equations describing the Milky Way. At the center of the galaxy lies a black hole 4 million times the mass of the Sun, Sagittarius A*, a gravitational anchor around which Earth becomes a nearly invisible presence. Beyond it, the galactic disk stretches 100,000 light-years in diameter. And surrounding all of this, the dark matter halo extends even farther, a ghostly sphere that dwarfs every world orbiting within it. Against such vast structures, Earth becomes a speck that cannot be plotted, a world whose physical size dissolves under the weight of cosmic distance. It is easy, in the face of such immensity, to imagine that the planet is insignificant, a fragile stone drifting through an indifferent void. Yet humanity does not experience the universe from the outside. It lives on the inside, tethered to this small world by breath, memory, and meaning. On Earth, scale changes. The ocean becomes an entire horizon. A mountain becomes a continent rising through cloud. A forest becomes a labyrinth of life woven through centuries. Earth shapes perception not through size, but through detail, through the closeness of its landscapes and the richness of its living forms. In this way, the planet occupies two different realities. Cosmically tiny, emotionally vast. This contradiction lies at the heart of what it means to live on Earth. It is a place that can vanish in a galaxy map, yet it holds the only known chemistry that has awakened into awareness. It is a world that has no significance to the orbital mechanics of the Milky Way, yet every human emotion, story, and thought has unfolded upon its surface. In all known space, Earth remains the single point where matter has learned to observe itself. Life, with its fragile cells, its relentless evolution, its branching complexity, transforms the meaning of the planet. Through biology, Earth becomes more than a rock. It becomes a cradle. Through consciousness, it becomes a vantage point. Through memory, it becomes a vessel capable of giving scale to the infinite. When astronomers look outward, they measure the universe in light years and parsecs. But internally, through the lens of experience, life measures with a different set of tools: awareness, curiosity, wonder. These forms of measurement cannot be graphed, yet they shape the universe just as strongly as gravity shapes orbits. This is the paradox of the human condition. A species so small that it disappears into cosmic statistics, yet capable of asking questions that span the boundaries of the observable universe. Earth's meaning emerges from this tension. It is fragile, a thin crust wrapped in air, vulnerable to change, drifting through a place where survival is not guaranteed. But fragility is part of its significance. A world that should have been silent instead carries voices. A world that could have remained barren instead hosts an unbroken thread of life stretching back nearly 4 billion years. From simple cells rising in ancient seas to modern minds able to contemplate the scale of galaxies, Earth has nurtured a lineage of intelligence that now peers outward, trying to understand the place from which it began. When compared to superclusters or the cosmic web, Earth is too small to chart. But in the search for meaning, it becomes something far larger. A reference point, a home, a reminder that significance does not follow the rules of mass or volume or gravitational reach. Instead, meaning arises from relationship, from the way life interacts with its world, and the way consciousness transforms the perception of scale. If the universe is defined by distance, then Earth is defined by presence. If the universe is expansive, then Earth is intimate. If the universe is silent, then Earth is a rare place where silence breaks into language, music, and thought. The emotional weight of this contrast shapes humanity's sense of existence. Many find a kind of humility in Earth's smallness, an understanding that the universe does not revolve around this world, nor around the species that walks upon it. Others find a deep sense of value in its uniqueness, the knowledge that even if Earth is cosmically tiny, it may be cosmically rare. Across billions of light-years of space, no confirmed life has been found. No second Earth has yet revealed itself with the clarity needed to declare that consciousness is a repeating pattern rather than a solitary event. Until one appears, this planet stands alone as a luminous exception in an otherwise silent cosmos. It is this silence that shapes the emotional dimension of Earth's scale. A planet that is small in size becomes immense in meaning when placed against a universe where meaning is difficult to find. In this context, the measurements of galaxies, clusters, and superclusters take on a new character. They become not just scientific achievements, but philosophical mirrors. Each new discovery pushes Earth deeper into insignificance physically, yet deeper into significance emotionally. Each larger structure dwarfs the planet's size, yet elevates its role as a singular home of life. The possibility arises that Earth's true scale is not defined by kilometers or mass, but by the consciousness that emerged upon it. That awareness itself is a kind of cosmic enlargement. Through observation, Earth influences the universe indirectly, giving form and meaning to structures that would otherwise exist unnoticed. A galaxy without observers is a galaxy without story. A universe without consciousness is a universe without scale. By this reasoning, Earth becomes not the smallest of worlds, but one of the most meaningful, not because of what it is physically, but because of what has unfolded upon it. Even the latest measurements of cosmic expansion, the tensions, the uncertainties, the unresolved parameters, hint at a deeper truth. The universe may not be a place where size is fixed. It may not even be a place where size is absolute. Instead, scale may emerge from context, from relationships, from the interplay between matter and mind. In this shifting landscape, Earth holds a unique position. It is a stable point in a universe of expanding distances, a familiar reference in a cosmos where constants may not be constant forever. And it remains the only world where the question, "How large is the universe?" has ever been asked. As the chapter closes, a final reflection settles across the dark. The universe remains vast, perhaps infinitely so. Earth remains small, perhaps impossibly so. But between these two truths lies the space where meaning is born. A world can be tiny and still contain oceans of experience. A planet can be fragile and still cradle a civilization capable of contemplating the cosmos. Earth becomes not a dot in space, but a vessel of awareness. Not an isolated rock, but a source of perspective. Not a small world, but a vast one, measured not in distance, but in meaning. And so the journey ends where it began, with a planet suspended in darkness, luminous not because of its size, but because of the life that calls it home. A small Earth in a boundless universe, carrying a scale all its own, one forever just beyond the reach of measurement, and forever within the reach of wonder.